Good morning. So today it is our alkanes part 2. Yesterday we completed hydrogenation. Today we are going to concentrate on some of the very important reactions as far as exams are concerned for preparation of alkanes. One of the most important reaction, let me name, is Wood's reaction. Similar to Wood's are Wood's Fittig, Ullmann, and Corey House. Then we'll move to coal-based electrolysis. So these are our basic targeted reactions for the day. Let's start with our work. Here it is. So, as I said, today we are going to deal with certain important preparatory methods for alkanes. First of this we are going to deal is Wood's reaction. Wood's reaction. Then we'll have its slight modifications here and there, which are Wood's Fittig reaction, then Ullmann and Corey House. Corey House in current date is very important as it is influencing the preparation of alkanes by different methods day by day. It is one of the youngest reaction of hydrocarbon chemistry, and still a lot of research is pending on it, but is still regarded as one of the best methods for preparation of desired alkanes. So let's start with Wood's reaction. Wood's reaction and coal-based electrolysis reaction are almost 150-year-old reactions. They are very old reactions, they're ranging over a century, and are still important and still considered worth studying and teaching. So you can understand how important they have been in the alkane chemistry. So what is Wood's reaction? Well, Wood's reaction, to start with or to define with in a one go, I can say it is a coupling reaction. Whenever we use this term coupling reaction, we want to say that there is a carbon-carbon bond formation in this reaction. There is a carbon-carbon bond formation in this reaction. Now, how is there a carbon-carbon bond formation? To write the net reaction for Wood's reaction, I can write it as, let us assume there is some R1X. Okay, then there is some, let me say, sodium. Then there is R2X. What I want to say that R1, R2 may be same, may be different, but still I am representing them as R1 and R2. Compulsorily solvent used is something like dry ether. Why the condition should be dry and all we'll discuss later. Okay, in a very basic and a layman pattern, I can write something like this, that NaX is removed, NaX is removed and R1, R2 is combined. But there is no such compulsion that it is only going to be a removal from R1, R2. Under the same conditions, I can have R1 and R1 coupling. Okay, there is equal probability at a point of time. R2X, there is similar probability that by similar pattern, by removal of NaX, I can have all the three combinations. Okay, and we cannot practically control that only one type will be obtained and others can be totally subsided or can be totally neglected. That is not practically possible. Reactions and chemicals, they go by their own thermodynamics. We cannot control them like that. So, this is what was said to be Wood's reaction. It is a coupling reaction in presence of active metal sodium of alkyl halides forming alkanes. Okay. Now, as I said, it is a coupling reaction. Let me introduce you to the word organometallic. Organometallic compounds are those compounds in which in which metal is directly connected. Metal is directly bonded to negative charged carbon. Please do not go by organic and metallic. That organic compounds having metal is certainly not the definition of organometallic compounds. Organometallic compounds are only when metal is directly bonded to negatively charged carbon. If it is just that carbon is connected or organic matter, organic compound is having a metal, then you can have CH3CH2OLI, CH3COONA type compounds also as organometallic compounds. But let me clarify this very, these are not organometallic compounds. As in them, the metal is connected to oxygen and not to carbon. For a compound to be organometallic, metal has to be connected directly to carbon, not to any other atom. So then what is an organometallic compound? Yes, organometallic compound, I can have a general representation as Rm. I don't know metal is a divalent or a monovalent, but just a representation when R is directly connected to M. Okay. Now for examples, I can say a CH3CH2Na. Yes. CH3CH2Li. Yes. PHMgX possible. Me2Culi. Yes. Valid. Okay. Any R2, if I say general, R2ZN, yes. ET4PB, very famous, tetraethyl lead, is also an organometallic compound. Okay, so see the difference in the two. Here, C minus is directly connected to metal. It cannot be an organic compound having metal. It has to be directly carbon minus connected to metal. One of the famous compound, there are so many, but I'm just particularly interested in this particular one. One of the very famous compound of organometallic series is ferrocene, in which iron 2 plus is sandwiched between two cyclopentadienyl anions. Now, just to represent their force of attractions, I'm using this type. It is not a covalently bonded steric system. It is like a bread sandwich. Consider these two cyclopentadienyl anion rings to be planar like a bread. Okay, and this Fe2 plus is the filling of the bread sandwich. It is in between the two breads. So it is a layered complex. It is a layered complex. Can we have a multi-layered complex? Yes, you can have a multi-layered complex. Like again, there is Fe2 plus, again there is a ring. These type of complexes are quite common with cobalt and chromiums. But these are also examples of organometallic compounds. So, what was the relation? What is the point of discussing organometallic compounds in Wood's reaction. We were targeting Wood's reaction. Then we went to discuss organometallic compound. There has to be relation. Yes, certainly there is. There is a relation of organometallic compounds and woods. If you see alkyl halide and sodium on the way in the mechanism, in the reaction conditions, certainly there is formation of RNA in this particular reaction. Okay, there is RNA formation in this reaction, but what happens is it is so reactive that it it gets consumed there itself. Due to its reactivity, it gets consumed there itself. Therefore, we are unable to isolate RNA. And there is the difference between Grignard reagent and organosodium organometallic compounds. How can I say that? What is the point? Why I'm saying this type of thing? See, basically in organometallic compounds, when I say RMGX, there is a negative polarity on this and a positive on this. Or if I can generalize, in case of RM, where this is positive on metal and negative on carbon, then what happens in this particular thing is this R, which is incapable of having a ionic linkages, it always prefer only covalent linkages. Okay, here in this polar covalent bond, carbon always want to have more and more covalent character instead of ionic character. Okay, what does this carbon wants? Carbon wants more and more covalent character because that is its characteristic. Carbon prefers covalent bonds over ionic bonds, so it always wants to prefer covalent character, high covalent character bonds over ionic bonds. Now, in this particular bonds, that is the carbon and metal bond, as electropositivity of metals increases. Definitely the electronegativity gap between carbon and metal will also increase parallelly. So as electropositivity of metals increases, the percentage covalent character decreases. And it decreases where? It decreases in the RM bond. It decreases in RM bond. This is a fixed trend of organometallic compounds as and as these metals become more and more electropositive. The percentage covalent character, okay, the percentage covalent character in the carbon metal bond decreases, which makes organometallic compound less stable and thereby more reactive. This is a fixed rule for organometallic. They always want less electropositive metals, say bonding, so that they can have more covalent character. This particular point is so obvious that yes, in Quarry house, I'll again repeat this point that a less electropositive metal, a less electropositive metal always displaces more electropositive metal, okay, always displaces more electropositive metals from organometallic compounds. Less always displaces more electropositive metals from its compound. This is due to the covalent character search. Correct? So coming back to Grignard, coming back to Wood's reaction. Let me first suggest what is the mechanism given for Wood's reaction. Now, for Wood's reaction, scientists have suggested that it follows two different mechanisms. Two different mechanism. It can be a free radical mechanism, well and good. It can have ionic mechanism, carbon ionic mechanism. Both the mechanisms have been accepted by equal importance. Nothing as such has been fixed. I'll explain both. Say for radical reactions, the first step is sodium will release electron and will form Na plus. This whole thing is taking place in dry ether. Why dry ether? I'll discuss later. 5 minutes more. So dry ether, sodium plus, and one electron is released. I want more electron. I can have two sodium. I can have three sodium, whatsoever. Now, if I say these are two electrons, then see alkyl halides, which has del plus and del minus polarity here. When two electrons goes to this one alkyl halide, two electrons goes to one alkyl halide, this plus will accept two electrons and will become minus. X is also minus. Correct? Those two sodiums which we have written in top reaction, first reaction, when combined with this, we will have Rna plus NaX. See, this is our organometallic compound. And a very important thing that you need to observe is carbon here was del plus, carbon here will be del minus. So there is a reversal of polarity of carbon from alkyl halide to organosodium compound as plus to minus. This particular phenomena is known as ampolang. What is ampolang? Reversal of polarity of an atom in a reaction is known as ampolang, and there is an ampolang in organometallic reactions, as you can see. Now this RNA will combine with next molecule of alkyl halide. Reaction is expected to be binuclear substitution. R attack, and we'll have combinations like this. Correct? Now it was said that how, oh, I just wrote it in the opposite direction. I explained ionic under radical, so let us interchange the headings. Let this be ionic heading and let this be radical heading. So what about radical? In case of radicals, starting point is same. Similarly, we will have two Na plus and electrons. But these two electrons will not go to single alkyl halide. They will be distributed between 2 moles of alkyl halide. Okay, solvent is same. So I will have two radicals along with X minus. Similar, this halogen is gone. R is plus. When plus accepts one electron, then it becomes radical. When plus accepts two electron, then it becomes carbon ion. So now these two R dots combine with each other and form RR, and similarly 2 Na plus combining with 2 X minus and will form twice NaX. So both could explain the coupling products R R with equalities. A question might come into your mind that which one should I prefer for questions? My answer is either. Either, whichever you find to be comfortable in, whichever you think that you can handle with more confidence and ease, prefer that one, because all possibilities of a reaction, whether I talk about the yield, whether I talk about the overall net reactions, or I talk about the side reactions, byproducts, all factors can be explained by both the mechanism. So no need to bother, no need to be worried that should I do each question with both? No. Just do with either. Either with ionic or with radical, you can end the question to the same answer. Just to strengthen my point, let me explain one particular observation. One particular observation. Side products. How would I explain side products which are disproportionation alkene and alkane by disproportionation? How can I explain these from these two mechanisms? So let me explain. For this explanation, let us assume for both reactions that this R is ethyl. Okay, let us assume that R is ethyl. If R is ethyl, then here CH2H, CH2X plus CH3CH2Na. This can also act as a base, na? So when this base attacks beta hydrogen, then instead of direct substitution, we will have CH2 double bond CH2 plus CH3 CH3 and NX. Correct? And from here, I can say that coupling yield will be 1 degree Rx, then 2 degree Rx, and very poor with 3 degree Rx. Because in 3 degree Rx, this type of coupling would be negligibly possible, and instead the above mentioned byproduct mechanism, which is by E2, will dominate. And that in fact is found to be an observation true. Have the same assumption if R is ET to explain the byproducts here. CH2H, CH2X plus CH3, CH2Na. Assume that this is a radical. Okay, so this radical will now attack, and here similar radical mechanism, and we'll have CH2 double bond CH2 plus CH3 CH3 plus NX. Same mechanism, same products by different mechanism. But the point that can this explain the order also of the yield? Yes, it can. Yes, it can. How? See, this particular coupling product is observed by the radical combination reactions. And this is radical downside, this is radical disproportionation reaction. Okay, now we already know that a radical combination is easy when the radicals are small, are less substituted, and as the radical becomes bulkier, then radical combination becomes less and less. As they become substituted, then radical disproportionation dominates 3 degree, 2 degree, 1 degree. Okay, so the same point that the yield of a combination product which gives the required hydrocarbon order is same whether you go by ionic or you go by radical. Both the reactions again justify that if alkyl group is kept same, alkyl group is kept same, then order of ease of Wood's reaction is Ri, Rbr, RCl. RF is not much taken into experiment, is usually avoided. So we'll prefer RI, RBR and RCl. Okay, and the reason is bond dissociation energy. Less the bond dissociation energy, better the reaction will be. Okay, now what happened that in this woods, the organometallic formed is organosodium. Sodium being more electropositive will have more ionic character in this bond. So organosodium formed are so unstable, are so reactive that they immediately attack whichever alkyl halide they found in the reaction condition. As a result, I can practically fail to isolate RNA. If in place of sodium I would have used some less reactive metal like magnesium and all, then yes, isolate we are able to isolate organomagnesium compounds by the same reaction conditions, because magnesium being less electropositive than sodium will have a more stable organometallic compound. Okay, correct till here. Definitely, if I one more observation that if I keep same halogen, if X is same, okay, then reaction will fail for vinylic halide and pH halide under normal conditions, under normal woods. We cannot take we cannot prepare a combination of these two compounds under normal woods. We can use other metals, we can change the reaction conditions, and then it is different. But if simply woods, then not possible. Okay. Now, what is the classification of woods? What is the classification of woods? Well, woods I would like to classify as simple woods, mixed woods, and third, I would say intramolecular woods. Intramolecular woods. Okay. So, what is simple woods? If, as per the net reaction, R1 is equal to R2, okay, then it is simple woods. In simple woods, even number, even carbon number alkanes are prepared. Okay, these will be symmetrical in nature. In case of mixed woods, I can say R1 is not same as R2. Okay, odd carbon number alkanes are prepared. Correct? Usually unsymmetrical fission of alkane. What I want to say, for example, agar N-pentane is what I want to prepare, then either I have to go for ethyl propyl halide combination, or I have to go for butyl methyl halide combination, but both are unsymmetrical. They are not same, they are different. Okay, very important point is with related to their yield. Here we have a good yield, here we'll have a poor yield reaction, and this is why we prefer woods to form even carbon containing alkanes rather than odd carbon containing alkanes, because the yield will be better. And I think you can understand it from the net reaction that why yield will be better. Only one type of compound will be obtained. Na? There is no such three types of compound. All three will be same compound only, and thereby definitely percentage yield of any one compound is dominating. In case of mixed, I have these three combinations, so yield of any one will be less. Coming to third type, intramolecular Woods reaction. Let me tell first, it is a very good yield reaction. Good yield reaction. Why? Because intramolecular reactions, if orientations and reactivities are achieved, are supported by entropy factors. Are supported by entropy factors. In an intramolecular reaction, it is not that more number of molecules are combining to give less number of molecules, so entropy of a system is decreased. Here, if not increased, at least remains unchanged, and therefore intramolecular reactions are preferred wherever possible. In case of intramolecular woods, the most common important thing is you can prepare you can prepare a smallest possible ring like this by woods very easily. Cyclopropane. You can prepare cyclopropane easily by this method. So it is a very good method of preparation of cyclic rings. Okay, till here it is okay. In 2005, J 2005, there was a question, very famous, very normal. Okay, there was a question in J 2005 based on this the thing I was telling, that it is a reaction which is used for forming small rings which otherwise are not that easy to prepare. Okay, this is in fact regarded as a very important success of Woods. This was a very standard experimental setup that has been used by Jay to frame the question. They gave options like bromine is easy to remove. So could it be something like this? If chlorine people consider easy to remove, could it be a combination like this? Okay. Could it be a combination of one chlorine, one bromine? But none was correct. The correct answer is one and only bicyclo structure, bicyclobutane. Okay, this is still people sometimes, particularly students, do wrong, that how can a strained 2-3 member ring combination will be formed. To surprise you, I would like to add the yield of this reaction is 93 to 96 percentage, which is extremely good. So the purpose of intramolecular wood is to form such type of cyclic and bicyclic compounds. There are several strain rings which have been obtained. And why we obtain this? Because of a very unstable nature of RNA. It attacks wherever it finds easiest and best to attack. Intramolecular attack are certainly faster, certainly easier as compared to inter. Okay, so this is how we can use it. The other type of question, which was asked, I would say, in Olympiads also, but it needs a question refining. A language should be very clear. Which of the following, sometimes they use the word hydrocarbon, sometimes they use the word alkanes. So I'll first go by the word alkane. Which of the following alkane cannot be prepared by Wood's reaction? I have seen this question in so many, I would say, different other institute paper or our inside Sri Chaitanya paper sometimes. But I would strongly suggest to avoid this question without a proper language. Cannot be prepared by Wood's reaction. To add it further, I can say, if I what should be the added thing? In good yield. Sometimes they just forget to write this. Okay, this If not present, please refer the question. I am writing options. If this is not mentioned, then what will be the problem? I have seen these type. Okay, you cannot say anything if in good yield word is not mentioned, because I can prepare all of these in, I would say, reasonable yield. This, yes. Okay, I can prepare this. I can prepare this by the symmetrical bond fission about C2-ethyl halide. I can prepare this. I will not from here, I will go from here. Yes, but this will be poor yield because it is a mixed woods. Okay, here I can have symmetrical fission from here. That is my one choice. Or why can't I have a intramolecular from here or here? This is my first choice. This is my second choice. This is my third choice. If I want to go for intramolecular, I'll prefer the intramolecular. In good yield, I'll prefer the intramolecular ring formation reactions, and I can have a good yield. Similarly, this cyclohexane should also not be in the question because I can prepare it by intramolecular Woods reaction. What's wrong with that? So, if I'm asked particularly for this question, I'll answer only B. And my point remains because it is a mixed woods reaction that has been used there. Otherwise, there is no point in defining what is the good yield in this type of question. Okay, so be careful about the language. Otherwise, this question makes no sense. Okay, when it was asked in Olympiad, they were very clear about the language by a combination of only one type of alkyl halide. This type of thing, something they have mentioned, so it was good. Now the point comes, what are these other reactions? If I go to my introductory page, I have said that we'll do Woods and then we will do some other reactions like Woods Fittig, Ullmann and Quarry. B, C, D first I'll add. They are just slight modifications of Woods reaction. Okay, they are just modifications of Woods reactions. What modifications? That if you keep on changing the metal used, if you keep on changing the reactant used, you will have different reaction. Woods Fittig is when one of the component is aryl halide. Yes, with sodium it will be difficult, certainly, but it is obtained. In case of Fittig, when both the reactant used are aryl halides, in dry ether heat certainly अब यहाँ ज़्यादा लगेगी. Okay, Ullmann, when we use aryl iodide in presence of copper, okay, it is a particular reaction. When we use this reaction, when we have this reaction in presence of copper as a metal, then the reaction is called Ullmann and a coupling reaction. So these are other modifications. Why we have been so particular about dry ether? Okay, condition should be absolutely anhydrous. Conditions should be absolutely, totally anhydrous. Otherwise, sodium will react with the moisture, causing explosions and liberation of hydrogen gas. So conditions of the reaction should be absolutely anhydrous. Now, as we have seen, the drawback of Wood's reaction, the biggest drawback of Wood's reaction is that you cannot prepare a mixed type of compound, a mixed type of alkane. To overcome this problem, there was an introduction of Quarry House reaction. Quarry House reaction. Let me tell you, these are two different scientists. They have worked in two different parts of the world. Okay, House was from Georgia Institute of Technology, MIT. Okay, first he was in MIT, then he moved to Georgia Institute of Technology. Corey was from Harvard. They were working from other sides of the world. They were not working together. They were working separately, but coincidentally they ended up with the same type of conclusion, and so together they have won the Nobel also. Okay, together Corey and House, together they have won the Nobel in 1990. This reaction, due to this reaction only, they have won the Nobel of 1990. Okay, so uh, Corey and House, and as far as I remember, I think Corey is still alive. He's still working as a organic chemist. Okay, so what is the reaction? They have just modified the organometallic reagents. They said that take R2CuLi, attack it with some other alkyl halide, and form a mixed combination of RR dash RCuLix. ये coupling reaction. This was a Gilman reagent. Gilman was also a scientist, but his reagent was proposed far back, somewhere around Grignard. Okay, but at that time it was not recognized. Corey and House found that this reagent can have a controlled behavior and can be used for preparation of odd number carbon alkanes. So, how to prepare Gilman reagent? Preparation of Gilman reagent. It is prepared from alkyl halide taking lithium, like sodium, RLi plus LiX is formed. Then this RLi is treated with CUI. As I have told you, that I'll repeat this in Corey House, I told that also, that this alkyl group will shift towards copper to have more covalent character. With lithium, it is having more ionic character. But as copper can always expand its octet, it can have one more coordinate bond. So we'll have RCuR minus Li plus. Okay, so basically it is a cuprate complex. It is lithium dialkyl cuprate complex. This is what is Gilman reagent is. It is represented as R2CuLi. But as you can see here, carbon is connected to copper. Okay, now what is Corey House? Corey House is not preparation of Gilman. It is always picked after that, that this RCuR Li plus is now made to react with R dash X, and a direct expected to be SN2. The reaction is expected to be SN2 till date, as the research is still on, so there is no conclusion final made that it will always be said so or not. This type of coupling. Here, this should be primary, it should be allyl, benzyl, etc. for good yield. We'll again avoid here 3°, but you can have 3° here. Okay, so that is why Corey House is important, because it is easily overcoming the limitations which were proposed, which were present in Wood's reaction. So this is why Corey House is an important reaction. Other factors are found same, that this X should be Cl, Pr or I. Fluorine is definitely not studied much. Okay, this Gilman reagent attack has so varied, what should I say, varied observations. Even this reaction is found to be successful to a certain extent on vinylic compounds. It is found to be successful on aryl iodides, which is very unlikely for an SN2 reaction to be, and therefore it is still used the term expected to be still not confirmed. Or it may also follow more than one mechanisms, God knows. Because it is under research reaction, so we cannot comment anything conclusive about its mechanism. But yes, it is very important. It is a very good yield reaction. It is in fact preferred for preparation of odd carbon compounds or a mixed series of combinations to be taken. Then go for Quarry and House reaction. Okay. Next, let's move to another very important reaction called coal-base electrolysis. Again, a very important reaction for our exams, coal-base electrolysis. It is an electrolysis of aqueous salt of sodium or aqueous solution of sodium or potassium salts of carboxylic acids. Okay, we can use either. For my further proposal, I am preferring potassium salts. So how to write the net reaction? R1COOK plus R2COOK. They are all aqueous, that is solvent is water. When electricity is passed, electrolysis is done, then there is a combination of R1, R1, R2, R2, R1, R2. Besides this, there is a release of K2CO3. Okay, so let us understand this reaction to core. First, how the reaction proceeds. Okay, how the reaction proceeds. So again, going back to the word mechanism. For mechanism, assume R1 is equal to R2 is equal to, say, ethyl. Okay, so we have CH3CH2CO OK aqueous. Under aqueous conditions, it will always undergo ionization to form CH3COO minus aqueous and K plus aqueous. Correct? This is our anion, this is our cation. Now, on anode, anion will be fixed to move. And always remember one thing, irrespective of the type of cell, anode compulsory is the place where oxidation reactions takes place. Cathode will have cation and reduction reactions take place here. Okay, on anode there is oxidation reactions, on cathode there are reduction reactions. So let us see anion. So CH3CO, when I say minus, this is the condition of electrons on oxygen. Okay, so and then I say oxidation takes place on this pole. What is oxidation? Oxidation is loss of electron. What is oxidation? Oxidation is loss of electron. So this becomes CH3, CH, oh, please excuse me, I took ethyl, CH3, CH2, CO, O. Now I will write one electron less. Now it is a radical. But radical on electronegative oxygen will be unstable. So this will decompose to CH3, CH2 dot, releasing CO2 gas. Correct? Now this CH3, CH2 dot, if goes for radical combination, if it goes for radical combination, then I will have ethane, from ethyl, sorry, from propionate salt to butane. If it goes for radical disproportionation that I explained in Woods, if it goes for disproportionation, then I will have CH3 plus eth. And certainly both the things are possible. As I have said before also, you cannot limit that only this type of thing is the only possibility. Okay, so both the reactions will take place. Same way, yield of combination will be better if it is a 1 degree radical than 2 degree than 3 degree, as and as these radicals become bulkier and large. Okay, as and as these become bulkier and large, definitely there will be loss of combination to disproportionation. If I'll go for bulkier and bulkier, there will be problem. Let's move to what is happening on cathode. As we have said, cathode will be associated with reduction. What moved to cathode? K plus. Under aqueous conditions, certainly there is a lot of water. Okay, there is lot of water here. So now when we go to this pole where reduction, that is acceptance of electron, will be there. To balance, I am adding 2 electrons to K plus. If you check the standard reduction potentials, under aqueous condition, then H plus is easy to reduce. Than K plus. And it is such an obvious behavior. Potassium is a metal. Its tendency is to lose electron. Hydrogen, is a non-metal. Its tendency is not as much to lose electron like potassium. So it is the H plus that will accept the electron. If H plus will accept electron, it will become hydrogen gas, and 2OH minus left will form 2KOH. So I have KOH at cathode, I have CO2 at anode. Okay, I have KOH at cathode, CO2 at anode. This KOH, aqueous, CO2 won't be able to escape, it will be absorbed by KOH, forming K2CO3 and water. See, there is formation of K2CO3. So what happens if there is a formation of CO3? Let me go back to my net reaction. Initially, in my reaction condition, there was salt of carboxylic acid with potassium. When the reaction is completed, there is a combination of salt of KOH and H2CO3. KOH and H2CO3. Okay. Now, carboxylic acid versus H2CO3. Then RCOH are stronger acid. Than H2CO3. That is a well-known fact. Okay. So if I dissolve RCOOK, it is salt of weak acid RCOH plus strong base KOH. If I say I have K2CO3, it is also salt of weak acid H2CO3 plus strong base. So there will be hydrolysis of these salts under aqueous condition. Okay. What would be the resultant pH? I can say pH of K2CO3 aqueous solution will be greater than pH of RCOK aqueous solution if the concentration initial were taken as reference same. Okay, because this is a weaker acid. base remaining strong, as and as the base acid component becoming weaker and weaker, the pH will become more and more alkaline. So, a very important conclusion comes that with completion of coal base electrolysis, with completion of coal base electrolysis, what will be observed is pH of the electrolyte will increase. Okay, pH of the electrolyte will increase. Second very important point that usually people make error is, see, irrespective of the acid used, cathode always liberate hydrogen. Okay, see observations. Anode alkane, cathode hydrogen. Correct. But for formic acid salts, even anode releases hydrogen. If it is a formic acid salt, then even anode releases hydrogen. Okay, so read question very carefully. If the question says which of the following acid will release hydrogen at anode, then your answer is formic acid salt. If the question says which of the following will release hydrogen at cathode, then it will be all salts. It is not just formic acid salt which will release hydrogen at cathode. It could be any salt taken. Okay, so please read the question very carefully. They are asking hydrogen at which particular electrode. Clear? Woods, like woods, coal base can also be called simple, it can be called mixed, or it can be intramolecular. All three types, same way, could be there. Similar type yield better, poor, good. Okay, you can have intramolecular woods. Yes, certainly. If I could repeat the J 2005 woods question for coal base, if we are asked coal base electrolysis of this particular compound, we'll answer this only. Okay, so this is how coal base electrolysis could be used. A slight modification of both of my reactions from chapter alkane, a slight modification, okay, towards alkene. Both the above reaction could be even used for preparation of alkenes. How? I would say vicinal dihalides in Wood's reaction form alkenes with same carbon count. Example, if I have CH3, CHX, and I go for Woods, see, the reaction will be intramolecular, and answer is 2-butene. Okay? Geminal dihalides form alkenes with coupling inwards. How? For example, if I had CH3 CHXNX, I take sodium in dry ether, there is a possibility that a reaction proceeds first by intermolecular coupling like this, and in the end, the above reaction, I will have 2-butene. Okay, correct? So this is how I can have alkenes using Wood's reaction. Here it is a simple dehalogenation reaction. If I am similarly taking coal-based electrolysis, let me take for succinic acid salt. In coal-based electrolysis gives ethene, right? CH2, COK, COK, coal-based electrolysis. Radicals will be formed here and ethene will be formed. Is it okay? And similarly, if there were gem, there is a possibility that yes, I can have something like this. Something like coupling alkenes could be formed. Is it okay? So this is how we can use Woods and coal-based electrolysis for the synthesis of alkanes. This is how we can use coal-based and Woods reactions for synthesis of alkanes. Both these reactions are of historic importance and are still relevant for varied types of questions. Okay, so that completes our preparation of alkanes and also concluding our today's lecture. Tomorrow, our target will be to complete the most important reaction of alkanes. In fact, I would say sole reaction which has been questioned in JEET so far, that is halogenation of alkanes. It has enormous possibilities of questionnaire. So please revise your notes for today's lectures and be ready for tomorrow discussion. Till then, take care, keep studying.